So welcome everybody to this Data for Good meetup in February. We're thrilled to have Yogi Schulz with us to talk to us about graph databases. Really cool technology that's really coming on strong and has some amazing potential applications. Before we get into Yogi's presentation, some of you are new, and some of you, just a reminder about Data for Good in Calgary. So we're a group of volunteers. We use our data skills for good. Our aim really is to help nonprofit and social organizations to harness the power of their data to really leverage their impact in the community. So we're the Calgary chapter. We're one of 9 chapters across Canada. Thousands of members, and we've helped a vast variety of nonprofits through many different types of events. And last year, we had a national datathon, which was really cool. So we brought together all the chapters working with the Nature Conservatory of Canada, and that was a great event. We hope to do more of those national events as well. So we've been around since 2013. So we broke through the 2,000 member mark over the last month or so, and so that's fantastic. We kind of work in 3 different ways. We do these larger events called datathons, which in better times when we could get together would be a Friday night, all day Saturday, and a Sunday morning, partnered with larger nonprofits that have a lot of data. We do smaller data core projects with organizations that have a data challenge. Bring them into one of our groups and get a bunch of volunteers like yourselves to help for a few weeks, a few months, whatever it takes. And then of course we have our monthly meetups on the 4th Thursday of the month. So please tell your friends about it. Sign up through Meetup, and there's our Twitter handle, and we have a national website as well, and the Calgary chapter is on that. So just reviewing some of our activities. So over the course of the years, and literally years, you can see all of our events on, if you go to Meetup, our Meetup site, and go on past events, go on the event tab and past events. You can scroll through that, and more often than not, the presentation decks, there's a link to the presentation decks. And over the last year or so, we've actually done the recordings as well. So the recordings are available. So if you missed a previous event or something attracts your interest, then please take a look at it. Last spring, as we were getting used to the pandemic and not being able to gather, we put together 3 micro datathons. So 3 of our meetups, we launched these micro datathons. So they still exist as past events, but they're really cool because there's data sets that were curated for each of these micro datathons. There's instructions, there's challenges, all kinds of great stuff. So if you want some practice, if you want to work on your data science skills, your data analytics skills, geospatial, data wrangling, whatever it might be, and you missed these or you want to do them again, just go back and look at those in our past events. Some of our data projects, usually we have 3 or 4 in flight at the moment. Right now we're working with the Alberta Law Foundation, the Canadian Cultural Mosaic Foundation, that Canadian Social Harmony Index. We're doing some data visualization of that survey data. We had the Immigrant Services Calgary come in, talk to us about a new application that they've launched to help immigrants get used to Calgary. and a bunch of people have volunteered for that as well. So lots of opportunities there. These are curated through you expressing your desire to volunteer. There's a survey, a form for you to fill in. If you go to our meetup site and go to About, in the description of Data for Good, you'll see the link to the form. So if you haven't already, please fill it out, and then we know that you want to volunteer. And then as we launch new projects, we can reach out to you. I talked about our datathons, the ones we've done over the years, and here in Calgary with Calgary Foundation, Distress Center, Arts Development, many others. They've been great and really beneficial to those organizations as well as us as volunteers, to really get to know these organizations and to be able to help them out to further their work in the community. And then all the other groups that have across Canada as well. So over the last year, we've been partnered with the Calgary Homeless Foundation. They have an amazing data set called HMIS, which is their Homelessness Management Information System. And we're kind of the first outside group that's ever working with them to get access to that data set for a datathon. Again, because of the pandemic, we have been challenged to do the face-to-face. But our plan now is that in the May timeframe, we're planning to have an online kind of virtual mini datathon. So not with all the data, but a limited subset of the data. We'll curate some challenges, put them out there. We'll probably do it on a Saturday. So it'll be like a datathon, but we'll be doing it virtually together. So look for that coming up in May. And then our hope, though, is by November, we'll be able to get back to our face-to-face datathon sometime in November. So that's it for me. So I'm going to stop sharing, and I'm going to turn it over to Yogi. Yogi's been with us before. He's a seasoned veteran of the Calgary data and technology ecosystem. I'll let him provide a bit more detailed background. But Yogi, it's fantastic to see you again. And I know the last time you were with us, you were talking about data visualizations and techniques, and that was really well received. And I know we'll get a huge amount out of your graph database presentation. So take it away.
Well, thank you, Jeff and Oscar, for inviting me back this evening. So I hope you'll find it interesting and informative to talk about graph databases. So let me just share this for one moment here. And how's it look, Oscar? And Jeff, rather?
Yep, no, it's looking good.
Good, we can see it.
Okay. Great. So as Jeff announced, we're here this evening for a quick primer on graph databases. So thank you for inviting me back, Jeff and Oscar, and looking forward to sharing some ideas here with you. Graph databases have moved from a topic of academic study into the mainstream of information technology in the last few years. Graph databases are designed to treat relationships between data entities as equally important as the data values themselves. Unlike relational databases, graph databases store the relationships among entities as explicit values. With relational databases, you probably know that you must perform a join before you can understand the relationships among data values. So graph databases hold data without constricting it to a predefined model in the way that relational databases do. So those are some differences off the top. So Zoom, Jeff has already handled that, so we don't need to talk about that. Just a moment on me. I founded Corvelle Consulting over 20 years ago. We're in the information technology related management consulting business. We've executed many consulting and project management assignments for our clients, most of whom operate in the upstream oil and gas industry. I write a column, regular column in IT World Canada. Some of you have perhaps read some of those, and the audience is mostly IT executives and managers. And I've presented it in the oil industry and at PMI and other places over many years. So let's talk about the presentation tonight. We'll start with some context about trends in information technology, and then we'll talk about the advantages of graph databases, explain why they're being adopted more, and where they fit into your work. Now, everything has disadvantages, and graph databases is no exception. So we'll talk a little bit about the disadvantages, which is mostly about the lack of maturity of the technology, and that turns into risk factors for your projects. And then I'll talk about the graph database vendors. We'll briefly profile the leading vendors that offer these products. And as always, we'll end up with some conclusions and recommendations. So the overall goal of the presentation is to enhance your understanding of graph databases, point you to some superior resources that you can explore in the future that will further build your understanding, and prepare you to tackle a graph database proof of concept in your organization if you can see an opportunity to apply this technology. So let's start off with the presentation context. There are three major technology trends that indicate that the adoption of graph databases will increase significantly or perhaps even dramatically into the future, because graph databases address the problems and opportunities created by these trends. And these trends are database management system developments. So these are developments that we can leverage to address business problems and create business value. And then there's the digital data explosion that I'm sure you're all experiencing in real time. And frankly, it's taxing the limits of relational database technology. And then there are emerging applications. These other trends are creating digital data volume explosion, such as IoT, social media, e-commerce, and they're also driving the emergence of new applications that benefit from the existence of graph databases. So let's just do a quick history. So to improve data management and data processing, as data volumes grew, database management systems emerged as a separate software layer between the operating system and the application in the 1960s. Previously, all data was stored in the file system associated with the operating system of the machine you were using. So the hierarchical databases, like you see this schema here, were the first generation of database management systems. They have a simple tree structure that's illustrated here. And the dominant DBMS, and perhaps the only commercial one, was IBM IMS, Information Management System. Has anyone used IMS? You can click the reaction button if you want, or a thumbs up. I'm not expecting many responses. Most of you are just too young. You probably never even heard of this product. But this was the beginning of time with database management systems. And from there, we moved to network databases. They were the second generation and offered a richer structure starting in the 1970s. Example products were Database, IDMS, and Total. And after that came relational databases. This is, I'm sure you're all intimately familiar with this generation. In the 1980s, they came into existence and have remained the principal DBMS that almost everybody uses in one shape or another or form. And the dominant products are Oracle, SQL Server, and DB2. Now, even though this is the dominant database, the reality is that the thinking around DBMSs and the development continued. And what we had after that is the NoSQL databases. So in the 2000s, we saw the emergence of XML databases, NoSQL databases, and the idea that databases didn't need to be as tightly structured in the tabular form as we're used to in the relational DBMSs. In the 2010s, databases that support JSON, the open standard file format, gained traction. We also saw the rise and the ultimate fall of Hadoop, a software framework for using highly distributed storage to process big data. So these are the 4 dominant types of NoSQL databases. I'm going to talk about each one just a little bit. The first one is the document store. These databases store each key beside a complex data structure, which is called a document. However, don't think about Word documents here when you hear the word document. In this context, a document contains a key array pairs or key value pairs. Example applications include catalogs, user profiles, content management systems. Example document NoSQL databases are MongoDB, Apache CouchDB, RavenDB, ArangoDB, and it goes on and on and on. The second type is the key value store. These are databases that store all the data as key value pairs. They're the simplest databases among this group, and they offer incredibly fast query and write operations. And example applications include user session details and preferences, real-time recommendations, advertising placements, that kind of thing. Examples of these databases are Redis, Memcached, Apache Ignite, and Riak. And then the third style is called the wide column databases. They store columns of data together instead of rows of data. And the databases are optimized for queries of very large data sets, meaning millions and billions of rows. Example applications include sensor data such as IoT, geographic information, time series data, logging, and other write-heavy applications. Example wide column NoSQL databases are Cassandra, HBase, and Scylla. And the last category here are the graph stores. These are the ones that we're going to focus on in this presentation today. And these types of databases store relationships explicitly alongside the data, and they also offer fast query operations. Example applications include artificial intelligence, fraud detections, roadmaps, social connections. Examples of their products, the major products are Neo4j, Allegro Graph, and Tiger Graph. So this is a whole new generation of DBMSs. Here they are, and then we're going to talk mostly about the ones on the far right, the graph data stores, and they're subdivided into the label property graph and the resource description framework databases. Now, the LPGs are easier to deal with, and the RDFs are richer in their capability. I should make a note that I'm not trying to suggest that these graph databases are going to take over the world and our DBMSs are history and will be abandoned. That's not the case. The reality is that both databases have their place in terms of the type of data that you're dealing with, and certain types of data gravitate you more towards our DBMSs, and other types of data structures gravitate you more to putting together an effective application based on a graph database. So depending on your application, you should choose one or the other. Now, another feature of the world is this digital data volume explosion. And I suspect every one of us is helping his or her organization try to cope with this explosion. So where is it coming from? Well, one of the places where it's coming from is the Internet of Things. So this is the explosion of industrial and consumer devices that monitor the performance of almost everything. These IoT devices have replaced lots of analog data recording devices, and they all generate huge volumes of digital data. And then we have the digitalization of our society. The most obvious example of this is the vast volume of digital data available on the web and its consumption by billions of people on the planet. Social media and e-commerce are creating huge volumes of digital data. The third thing is graphic and video data types. As you may know, originally digital data meant just letters and numbers. And then we've added graphics and video, and they've added orders of magnitude more storage. to cope with all of this. And the next category is digital transformation of business and government. Most organizations are actively working to enhance application functionality, fill in gaps in their application portfolio, and eliminate the remaining bits of paper and in the mountains of Excel workbooks that exist between their applications. These initiatives all add significant digital data volume. And I think we're all aware that during the last year, during the pandemic, everybody, businesses and government, greatly accelerated their digital transformation work. And the last trend that I want to talk about is the voracious demand for data that comes from data analytics. This has triggered a move to more, this has been triggered by a move to more data-driven organizations and has been accompanied by significant digital data volumes. So all of this leads towards graph databases. Now you may say, you know, this truck really illustrates what's happening in your relational databases. They're struggling to cope with the applications that data they're supposed to manage. Many DBMS advances and huge improvements in computing infrastructure performance introduced over decades are nonetheless straining or failing to handle this data volume. So applications as a solution that access graph databases can solve various data and application problems that are creating frustrations at the enterprise level. So let's have a look at the examples of some of these applications where a graph database can help: artificial intelligence, computing infrastructure monitoring, the customer 360 interaction analysis. This is the business of trying to understand all the relationships your customers have with your company. And there are typically many more than casual analysis suggests. Digital experience, enterprise search, fraud detection, knowledge bases. Organizations are finding that they need to capture the knowledge of individuals formally because they either, we lay them off, we fire them, they get headhunted, they retire. So we need to do something to capture that knowledge. Then there's the recognition of the value of metadata, master data management, natural language processing, product recommendation, social media influencer analysis, supply chain. All these applications process large data volumes and they require the querying of multiple tables or entities or nodes of relationships to deliver value. So they all benefit from using graph databases because graph databases deliver excellent performance for complex data analytics, simplified data ingestion and interaction with diverse data sources, and they manage vast data volumes reliably. So if you're thinking about an application in one of these spaces, do consider using a graph databases to make your application a success. So another thing that we always try for, Henry, it's for you. Apparently your heart is about to fail. And there's Amazon ready to deliver a new heart to you well ahead of a crisis. Now we all want to predict the future. And the most relevant applications include ones like production planning, logistics planning, financial planning, capacity planning. And when we try to be predictive, we're always going to find ourselves dealing with diverse data groups from many different data stores, huge data volumes, predictive data analytics, superior modeling capability, and fast response times. And now that's quite a mouthful, and that's quite a daunting list of requirements. So graph databases are specifically designed to handle these demanding requirements. So if you're encountering these in your work, think about using a graph database. Of course, if you're not encountering, then just don't spend money on something if what you're doing is currently working. Okay, let's talk about the advantages of graph databases. They're superior for managing highly interconnected data, for quickly producing concise results from complex queries. On the other hand, Relational databases are more general purpose and do well with processing a large number of relatively short transactions very quickly and efficiently. So for each of these advantages that we're going to discuss in the next few slides, I'm going to compare graph databases to relational databases. So we're going to talk about query speed, because we all want instantaneous results, no matter how complicated the query is. And the representation of relationships. This is really important because these two advantages surprise many, because we've grown up accustomed to thinking that relational data models do a great, or at least a sufficient job of modeling the business situation that we're trying to deal with. It turns out that relational models constrain our representation of the real world, and we really want something that's richer. Okay, so let's just spend a minute on graph terminology. A graph data model like this simple representation consists of nodes that contain the attribute data and edges that represent the explicitly stored relationships. So obviously the edges connect the nodes. A relational model consists of entities that consist of tables that contain the attribute data, and potential relationships are represented as foreign keys. Now, some of you may be aware that there's more to graph data models and relational data models than what I've shown here. And of course, you're right, but the main terms are enough to get us through this overview presentation. We're not trying to cram a data modeling course into the time that we have together here today. So let's make do with this admitted simplification. So let's talk about query performance. All end users are always impatient and expect quick response time. Nobody cares about how query complexity consumes resources, or how the vastness of data volumes that must be traversed requires elapsed time. And it's all in the interest of producing a result. And DBMSs work hard to meet these high expectations. So this graph shows that the performance of graph and relational databases is about the same until the depth of relationships that must be queried exceeds 9. So think of depths of relationships as the number of joins in our DBMS terminology. So for graph databases, the query speed is only dependent on the number of concrete relationships that must be read, and not on the total data volume in the database. So this focus on reading only the data that's directly related or closely related to the relationship being queried produces super fast results. So for relational databases, on the other hand, query speed is dependent on the number of tables that must be joined, the amount of data in every table being queried. This focus on tables and data volumes means queries slow materially as the number of tables and data volumes increase. While good index design and superior query optimization can reduce speed losses, it's often not enough. So if you have a lot of joins, then maybe that's another reason to think about a graph databases. So here's another table. So here we're looking at Oracle versus Neo4j, and you can see the difference grows, or the performance deteriorates, depending on how you want to view it, as you move down this table, as the complexity of the query increases. And indeed, it's not hard to get to the point where the query just plain doesn't finish. It just hangs. Obviously not a good place for anybody. Okay, now let's talk about the representation of relationships. Whenever a DBMS can represent the real world relationships accurately and avoid kludges or workarounds such as cross-reference tables or composite keys, it's easier for software developers to understand the organization of the data in the database. That ease of understanding leads to more accurate, reliable solutions with less development effort, and reduced effort and elapsed time to implement future enhancements. So for graph databases, the relationships are stored in the data alongside the attribute data, and this storage results in high performance queries. The graph model is a simple, this graph data model is a simple subset of a social network of music lovers. And here's a much more complex model for oil and gas production ownership used in joint interest billing. For relational databases, relationships are defined through the value of foreign keys or through software logic. Now, foreign keys are incredibly useful up to the point where they trigger too many joins or even force a self-join. At that point, foreign keys can cause a significant deterioration in query performance. Defining relationships through software logic makes it more difficult to understand the logic just by looking at the database schema, and creates significant software effort. So in this example here, we see the complexities that arise when a relational database has to deal with too many foreign key relationships. Okay, so let's look at representation of data structures. Whenever a DBMS can represent a real-world data structure as accurately as possible with the minimum number of compromises, more of the same benefits I just described on the last slide under representation of relationships can be realized. For graph databases, data structures are more flexible. In this example, you'll see that the number of boxes in the diagram is exactly equal to the number of boxes in the real-world model. This is a good sign of the ability of graph data model to accurately describe the real-world model. The data is still contained in tables, just like in a relational DBMS, and these table definitions and their relationships can be altered dynamically. So that's a big advantage. So a good example here is something like base Facebook comments or posts that can consist of any combination of text, images, video, links, and geographic coordinates. Now, if I look at the relational data model for the same situation, the data structure is more rigid. There are more boxes to represent the relationships in the real-world model. The data structures always consist of related tables that together define and contain the data available for the entities. The data structures rely exclusively on the value of foreign keys to represent the relationships, and the data structure must be defined in advance. As I think you know, making changes to data structures of relational databases always requires careful impact analysis and planning, and sometimes, or often, it even requires an application outage to introduce the change. Okay, so another example here is a relational model. The mint green boxes are the tables for the major entities, and the white boxes are the tables required to describe the relationships. Now, if I look at the same model in a graph context, we have the mint green boxes, and the white boxes are the relationships, and there are no tables to describe those. And here at the point of this cartoon is to remind us that graph data structures are good for representing real-world entities, their relationships, with few compromises, complexities, or contortions. Okay, so with all that goodness that I've been describing, there must be a downside. I'm sure some of you IT skeptics are wondering about that, and so you should. So there are some. In graph databases, we have rapidly evolving technologies, so customers need to be aware of patches and new releases and plan a response. Some of these products are difficult to scale, and that has to be addressed through software development sometimes. There's no standard language, like we're all used to SQL for our DBMS, and it's transferable mostly from one product to another, and the skills of a developer are very easily transferable from one environment to the other as well. Not so with graph databases at the moment. The lack of parallelism, some of these products can only handle one application or one active query at a time. We would view that as ridiculous in the world of Oracle or SQL Server. And there are missing operational features. As you know, we're used to a lot of tools that help us manage these databases in the relational world, and they're quite immature yet in the graph world. So these disadvantages should make us cautious about committing to deliver highly available, robust production quality applications on top of graph databases. Keep in mind that there are, however, that there are many valuable applications that exist that don't require these features. For example, many data science applications, data analytics applications don't require real-time response. And if they crash or the task doesn't complete normally, you can restart it without really creating any pain for anyone. So you may say, well, wait a minute, these are all solvable problems. And indeed, all these products are addressing these problems with truckloads of venture capital. All these venture capitalists are keeping in mind the recent Snowflake IPO. I don't know if you followed that. In September 2020, Snowflake opened for the first time at $120 a share and quickly climbed to $300 a share and finished the day at $250 for 112% gain in the single day. And all of these vendors of graph databases are very much aware of that. And some of the owners of those products are hoping for a similar payday anytime soon. Okay, let's look at these disadvantages one each in turn. So this high level of product development to address all of these that's going on is sometimes making it difficult to compare these products when you're shopping, because they're playing leapfrog with each other on a month-to-month, quarter-to-quarter basis. So high-speed data ingestion is about importing large data sets at high speed as opposed to days, so hours instead of days. Integrated data visualization, why access the database with yet another software package, or worse yet, export summary data to visualize it. So just have the data visualization right in the database. Native JSON and XML data storage avoids a lot of translation on import and export. NoSQL data structures means that there's support for all 4 types of data structures that I described earlier, not just one such as the graph. Specialized hardware, this is about chips that perform much faster than your general purpose CPU chips for application performance improvement. Supporting both property graphs and semantic graphs as opposed to just one or the other. Integrated machine learning algorithms, again, having the database have the functionality to support machine learning rather than having that export the data to that application. And document entity enrichment is about parsing unstructured data for entity values to store it as structured data. So these graph database products are working on all of these topics to improve the appeal and functionality of their software as we speak. So under the heading of difficult to scale, we should know that initially these products were all designed as a one-tier architecture, meaning they could only run on a single server, and even if you bought 2 servers, it couldn't take advantage of that. So now the vendors have introduced what's called sharding, and there's 2 ways that you can create these partitions of shards. There's a vertical or a horizontal. So it's a question of how you chop up your data so that you can distribute it across multiple servers so that you no longer have a severe ceiling of the maximum size of your application. So vertical partitioning is about separating columns into multiple tables known as partitions, and horizontal scaling is about separating tables into separating table rows into multiple tables, also known as partitions. So each partition has the same schema in that case, but entirely different rows. So this concept facilitates scaling so that you can introduce multiple servers to attack your application. No standard language. Let's look at this one. Now, as you know, all relational databases support the standard SQL. Now, some vendors have chosen to extend the SQL language for certain verbs that you need for graph databases. And here's one of the approaches that's done that. So at the moment, you see all of these different approaches to this, the Cypher query language, with the Gremlin. So Cypher is being used by Neo4j and promoted by them. Gremlin is a component of the Apache Tinkerpop project. Gremlin and SparkQL address different types of graph databases. And then a fourth approach is to simply add graph extensions to SQL. So some of the vendors even support multiples of these query languages. So the impact of this lack of standardization is that it makes it difficult to migrate from one DBMS product to another. And it also adds cost to train people to become familiar. So the direction of solving this problem is that the vendors are participating in ISO and W3C standards development efforts to get to a single story. So some people think GraphQL will be the outcome of all of this. Others say, no, it won't. So I don't know. Okay, the lack of parallelism. As you know, our DBMSs, they can handle multiple queries running at the same time. And you don't have to take a number and wait for the predecessor to finish their query before you can start yours. Some graph DBMSs have started to offer parallelism, others don't. So it depends, in your case, is this important to you, given the application you're working on? So be careful around that. Missing operational features. Most database administrators of relational databases take these operational features for granted. These operational features either don't exist as part of a graph. In the relational world, these operational features either exist as part of the DBMS or as from the products of a multitude of vendors that you can add to your RDBMS environment. In the world of graph databases, many of these features don't exist, are rudimentary, or are under development. And I've listed a whole swack of them here, and I'm sure you could add to this list from your experience. So be careful. If some of these are important to you, make sure you get a product that a graph database that actually offers that. Okay, so crafting an appealing NoSQL resume. Do you have any expertise in SQL? No, doesn't matter. Just write expert in NoSQL on your resume. I wish learning about NoSQL were that simple. You could simply declare it so. The cartoon, I think, illustrates that there's a career development opportunity for many of you to become more familiar with NoSQL databases of all kinds, and perhaps graph databases more specifically, because there'll be an opportunity there to enhance your career in short order, or maybe that's there already today. Okay, let's talk about the vendors for a minute. We'll talk about the top 10 databases by popularity and by popularity trend. So here's the first one. No surprise, Oracle is number one. Microsoft SQL Server is number 3. And MySQL, which of course is an open source product, is number 2. Don't know which of these you're using, but that's the story there. Now, if we look at them by popularity, so this is really more around, this first one. So essentially, this measure here is a frequency of mention ranking or buzz ranking. It doesn't have anything to do with license fee or dollars or that kind of thing. Okay, the top 10 graph databases, again, as a buzz rating. Neo4j is very much at the top of this list. The Microsoft Azure Cosmos is the graph database in their cloud environment. Now, Neo4j, of course, you can run it in a cloud as well, but many people until very recently have run it on their on-premise environments. So if popularity is important to you or part of your evaluation, then by all means look at this. Amazon Neptune is the graph database for the AWS environment. Okay, the top 10 document databases by popularity. This is the first of the 4 types of NoSQL databases that I talked about. And you can see that both Amazon and Microsoft have cloud versions here as well. MarkLogic used to be a leader here. I don't know why they seem to be going down a little bit. Beats me. Now, if you want to look at it by a trend over the years, again, Neo4j is at the very top and has been for many years, and Microsoft has recently moved into number 2 position. And ArangoDB and OrientDB are tied in 3rd place, 3rd and 4th place. So it so what this graph, of course, doesn't show is the number of instances or the number of end users or the volume of data that's being managed by these databases has grown exponentially in recent years, which is one of the reasons why I think this talk is valuable or useful for those of you, which is probably everybody, hopefully everybody's trying to keep up with IT developments. Here's a set of about 100,000 data sources full of bits of well data. Please consolidate and integrate them into one meaningful data warehouse. I don't know how many of you have been asked to tackle that as an assignment, but I think it's crazy. Often managers have no idea how difficult data integration is. In every case, data integration work is preceded by major amounts of data cleanup effort. So be very careful to manage expectation about how much effort and elapsed time and dollars it'll take for major integration projects. Project managers are often bludgeoned into committing to budgets and schedules before anyone has any credible idea of the issues the project will face to achieve the goal. So sometimes selling a proof of concept rather than the whole enchilada is the way to deal with this. Okay, so let's wrap up here. What can we expect in the near future? How is this going to evolve? And then we have some conclusions and recommendations. So I think there are a lot of the future software development in the world of graph database that are going to make these products successively more appealing to people and cause more organizations to adopt them. Response time is already wonderful, and I'm expecting that graph databases will increase their lead over relational databases. Data oceans, that's a term I've developed. If you guys want to adopt it, you're welcome to use it. What I think we'll see is that graph databases will continue to increase their ability to cope with, manage, and deliver value from skyrocketing data volumes. Flexibility. Graph databases features will enable applications to become more responsive to rapidly changing business requirements with lower cost and lower risk of creating an unplanned application outage. I think people will find that very appealing. Diverse data integration. Graph databases will further expand their already rich library of tools to integrate data from diverse sources. This will make the data integration software itself will become easier to use. Some of it is not that easy to use today. Point out illogical constructs to software developers, alert end users about data quality issues and data integration disconnects, and automate high effort, mind-numbing data wrangling work. So I'm expecting a lot of progress there. Systems development velocity. Graph databases will become packaged with components to boost software development productivity and accelerate acceptable software quality. The components include an increasingly capable integrated development environment and more productive data integration tools. We'll see more algorithm libraries associated with the graph databases, and they'll continue to include support for analytics, machine learning, handling data quality issues, and handling some kind of software inadequacies. Graph query language, I think we'll see the emergence of a single graph query language that over time, because all the vendors are being pressured by all their customers to work on this. And database operation, graph database will become more sophisticated and less tedious with enhanced tools for work automation, performance analysis, data access, contention alerts, workload and model management recommendations, data and application anomaly detection, query performance analysis, health monitoring, problem analysis of the logs themselves. And we're already seeing some developments in role-based security. Graph databases will include more features to support role-based security. And we're going to see hardware developments that will express themselves as more improved database management performance. So I don't know how many of these you've heard of, but I'll just quickly run over them. The non-volatile memory express, and what this is a standard for solid state disk drives to increase application performance and reduce recovery elapsed time after a power failure. User programmable solid state drives. We tend to view solid state drives as little black boxes that offer fast storage performance. It's easy to forget that they include a processor. So recently, some manufacturers have begun to provide an API to that processor. And that leads to thinking of SSDs as software-defined storage that can accelerate input-output performance. Field programmable gate arrays, adding these to a multi-CPU cluster can dramatically raise capacity, throughput, and performance for graph database. I don't know if you recently noticed that the company called Xilinx, Xilinx, was sold for $30 billion. They're the leaders in the industry that makes these. So what they do is they improve performance by offering a massively parallel processing architecture, pipelined parallel computations, and a much higher memory to CPU bandwidth with low latency, all in the interest of more performance. And I've written an article about these devices. I never heard about them until this year. So you can look that up on IT World Canada if you're interested. GPUs, I think most of us have heard about GPU chips they're really for matrix multiplication, and that's why they're used so frequently to accelerate graphic performance in games and business applications that require a lot of graphic manipulation like GIS and maps and those kinds of things. But it turns out that they're also very good for speeding up creating training data for machine learning. And programmable networks interface cards. Now, we all have those in the back of our computers. And again, the speed is likely to double from the current maximum of around 100 gigabits per second. And to avoid taxing server CPUs with packet processing, the emerging solution to this bottleneck is to add more processing capacity to these network interface cards. Now, I'm not a hardware expert, but all of these are on the radar screen for databases and data centers that are running out of capacity to deal with that data volume that I mentioned earlier. Okay, so what does all this really mean? What conclusions can I draw from this? Graph databases will grow in importance in the coming years due to their major advantages. More organizations are implementing one or more applications that I listed earlier, and the adoption of these graph databases is growing. That was the motivation for giving the presentation today, to provide everyone with some general understanding of this technology. And graph databases will coexist with relational databases for many years to come. I don't want anybody to get the impression that I'm announcing or forecasting the death of RDBMSs here. They're not going anywhere. I mean, they've proven their worth over many decades in almost every organization known to man. And RDBMSs are implementing some of the technology advances that graph database vendors have pioneered. So building graph database skills will enhance your career. I think that's the conclusion I want you to come to from this. So what are the recommendations that I recommend to you? So there's a review the resources at the end of the presentation. There are multiple slides full of links to articles that are relevant to this. And there are links to the Tiger Graph videos and to the big conference they held last year. Tiger Graph is one of the major vendors. And there's also links to the Neo4j Online Developer Expo. Lots of talks about how to make this work. And those of you who like to read Gartner, this is the relevant Magic Quadrant that this is all discussed in. And my recommendation to you is try a graph of database proof of concept. All these vendors offer you trial instances on a cloud somewhere. So try it out, see what happens. See if you can deliver value for your organization. And with that, are there any questions? Can you help us select and implement a graph database? Just do everything immediately and perfectly and don't make any mistakes.
That's great.
That's the end of the presentation. I'll turn it back to Jeff, but before I do, just so you see, here are the slides that contain the resources that are in the PDF that Jeff referred to earlier. Okay, over to you, Jeff.
All right, fantastic, Yogi. That's an amazing amount of information, and
yeah. So don't blink; you'll miss something.
Yeah, absolutely. And just to say again that a copy of Yogi's presentation and the recording of tonight's session will be available probably sometime later tomorrow on our meetup site under this February 25th event. In the comments section, we'll put links to those in there. Bunch of questions, Yogi. We're not going to really have time to handle all of them. I will refer people to your references, but you know they can also, I guess, give you a shout as well if they want a specific answer to a specific question.
Yeah, so they're welcome to send me an email. I was scrolling through this and somebody said, how do I translate my our DBMS data model to graph? It turns out there's a utility or a number of utilities for doing that. So that's a point and click exercise.
Okay, cool. That was one of the questions I was going to ask and answer for. So thank you for answering that one. There are some questions on sort of limitations around using graph databases, you know, for AI or ML and that sort of thing, as well as limitations on hardware requirements. I think you addressed some of that, but just any high-level response to that?
Yeah, so the AI and ML, some of the vendors, they beat their chest by saying, wait a minute, we've already got those AI, ML, and ML algorithms built right into the databases, so you can just issue a call statement and you don't have to develop those routines yourself and test them and prove them and all of that sort of thing. We already have them available for you in the database. So if you're after an AI ML kind of application, you should give preference to the vendors that offer that and probably engage in a bit of a confirmation that their algorithm is as good as their marketing literature claims it is before you commit to it.
Okay. Any comments on data virtualization as a way to bridge the various databases or models?
Okay, I'm not sure I understand that question. Again, the vendors here say, yeah, forget Tableau, forget TIBCO, just use the visualization software that we've built right into the data.
Virtualization, data virtualization.
Okay, thank you, Jeff. I misunderstood the question. You're observing me stumble because the vendors don't talk about that.
Okay. So
I'm expecting there's not much to be said there.
Okay, fair enough. For for Python developers, is there a particular preference for one or more of the graph databases to work with? Or is it just that's the, go ahead.
Yeah, the vendors claim that their integrated development environments are language agnostic. So whether you're using R or Python or COBOL, they claim it doesn't matter.
Okay.
Don't know, haven't tried it.
Okay. Question, what happens when you want to unwind embedded relationships?
Okay, so unwind embedded, I'm not even sure what that is. You don't mean recursive relationships, or do they mean?
Well, I think potentially, like, you know, in a traditional relational database model, you know, the relationships are pretty hard to manage if changes, you know, you're making changes to it. I guess the question is, in a graph database, is it easier to sort of change the relationships without you know, having major issues or problems?
So the answer is emphatically, the vendors, most of them beat their chest that you can make dynamic changes to the model while the database is up and running. So if that's what we're talking about, yes, this is a big differentiator.
Okay, and then I guess the final question is really not specific to graph databases, but the audience, I think, would like to get your view on what is the potential growth of data science jobs in Calgary from your perspective?
Okay, so there's a couple of things there. If this is really about question about how to land a data science job, I wrote an article about some strategies for doing that. So go look at that. And I'm seeing, in terms of back to Calgary and the opportunities, I'm seeing more and more oil and gas companies thinking about using these technologies within their upstream operation and to help them. And the untapped energy forum that you showed on one of your slides, Jeff, at the beginning of this talk, is where a lot of that discussion happens. And in the startup realm, I think we're seeing some startups that are trying to leverage this AI ML space for applications in many industries, not just oil and gas.
Yeah, and I would encourage everybody like to attend the YYC DataCon, right, where you'll get a lot of evidence about the growth of data science, and you'll see some of the companies that are using it and where it goes from there. So right. I would give an emphatic yes that there is huge growth and potential there as well. But there's, you know, the traditional data management world as well. And Yogi, you were saying you're giving your talk at the conference is going to be about navigating those worlds of data science and traditional IT.
My talk at YYC DataCon is about dealing with the interaction, sometimes heated and sometimes conflicting, between data scientists and the traditional IT organization, and how to minimize those conflicts and be more collaborative and harmonious in the working relationships. So thank you for helping to answer that last question, Jeff. You did a great job.
All right. Well, we're out of time, so we'll have to wrap it up again. Big thank you, Yogi, for all your insight and your experience and your wisdom about this. Maybe we'll have you back for a hat trick at some point in the future.
Yeah, maybe we'll do an update on graph databases.
Yeah, there you go. There you go. And thanks everybody for joining this evening, and we look forward to seeing you at future Data for Good events there. And take care, stay safe, and hopefully see you virtually at the data conference coming up on March 12th and 13th. Okay, bye now.